one day passed, so I will not recall all the details, but I still remind you that we consider an arbitrary variety y, non-degenerate in this linear space. And yesterday I introduced some invariants related to it, but to define this invariance, I first embedded y by the second Veronese map. And in this way I got a variety x, non-degenerate here, where E2 is the number of linearly independent quadratic equations. So this is the image under the Veronese map. And I explained why the invariants for y, which very often vanish and are not very interesting, become interesting for x. So I consider the following invariants. First of all, I consider the secant varieties of x, high secant varieties. And then at some step I stop. The first step when I get the ambient space, like this. I denote the corresponding superscript by K2, and K2 plus 1 is nothing else but the order of x, which I defined before that, and this generalizes immediately the notion of order for matrices. This is the last, the first secant variety, which is trivial, which is equal to the ambient space. And correspondingly, I had the dimensions of this secant variety. And I have secant deficiencies. So I know that we have this formula. This is the expected or maximal dimension because we have this equality by definition. And so this is of dimension sk. This is of dimension sk plus 1. N is the dimension of x. And so this is the maximal or expected dimension, but it drops. It can drop. And it drops by this number, which is called quadratic deficiency of y. K plus 1's quadratic deficiency of y. So these are three types of invariants which we associated with y. And there is the last one, which I call the origin of secant deficiency. So, and denote by L2 of y. So we can write that the first L2 deficiencies are equal to 0. But the next one is non-zero. And now I proved some general properties of this invariance, which already show that they are different from similar invariants which can be introduced for y before quadratic embedding. And I'll recall these properties. First of all, we always have this inequality. So this number, which is the analog of order of matrix, can never be very small. And this is the first difference. The second difference is that in this interval, delta k the function delta k is strictly monotonos. That means that we have strict inequality, inequality, but maybe then I should write like this. And this is again a big difference in comparison with the general variety, not quadratic embedding. And this shows that, after that I showed that if we draw here k, and here we draw delta, then this function, delta k, is always contained in a certain band, where here we have c equal to the codimension. Here we have L2, and this is parallel to this x, to the x delta equal to k. So this is 45 degrees angle. Sorry, so this should be disregarded, but I just to mark it. So we know that L2 plus 1, sorry, L2, no, L2, yes, yes. So these numbers, delta, the function delta is somehow behaves like this in this area. The graph is contained in this area. In particular, from this it follows immediately that we have this inequality, that we have lower bound for L2, which is the codimension, because otherwise we cannot place our graph within this band. And if we have equality here, then the function delta coincides with this line, with this ray. And therefore, in particular, k2 is equal to n, and delta k is equal to k for all k to k minus c for all k in this range. So the last one is equal to the dimension of the variety. Now so this gives a lower bound for this function delta, and now I show that very often there is an upper bound, which is also useful, and which means that in principle L2 can be very big, and then we don't get much because it may happen that all the deficiencies are zero, and this really happens. For example, if x is a curve of odd degree, then all the high defects are zero. But this is not a very interesting case, and now I prove by simple calculation that some bounds that can be helpful. And so the following, if you wish, theorem. Suppose that the codimension is not large. We have this inequality, for example. Then L2 is at most 2 times the codimension. You see that here we know that L2 is at least the codimension. But this means that L2 in this is contained in this interval. So we can hope that we get some interesting invariants. And this is a simple computation, because I recall you that by definition, since up to L2 all the defects, second defects are trivial, we immediately get the following formula. So this function, this dimension of second variety, grows as fast as possible. Yesterday I explained that the idea of all this method is that as the second we go along this chain of nested chain of second varieties of x, we catch up with the similar growth for z. So if we denote by z the second Veronese image of the ambient projective space, then we get a similar nested chain. But here the defects are rather big. Namely here we have this equality. And so this growth in this along this sequence is rather slow. And if the dimensions of this in this chain grow rapidly, which means that secant defects are low, then eventually we'll catch up with this sequence, and so we arrive at a contradiction. So here, by definition, we have this formula, and therefore, since we know that we have this inclusion, we conclude that here we can write the following inequality, which we know. I just explained how to compute it. And eventually we get this. This is the last secant variety, which is equal to the ambient space. And we know its dimension. It's the number of quadratic monomials. And so from this inequality we infer immediately that conclusion, if we have our inequality, we have a variety of small codimension, then from this it follows this inequality. That's the first observation, that we are in our range, and L2 cannot be more than cannot be larger than for the ambient projective space. But then we can write the following. We can keep the same thing and write this, and this is equal to, for the Veronese variety. This is easy to compute. Because this is the sum of the first L2 numbers, which and I recall that our defects for the Veronese are like this. So we know how to sum up the first L2 natural numbers. And so from this, immediately we conclude that just by solving up this inequality, we conclude that and therefore, so we proved this. And furthermore, this is a trivial computation without any ideas. And furthermore, we know that if we have equality here, so if for such an n we have L2 equal to 2c, then we know when this happened. This means that the corresponding secant variety with number L2 for z and for x is the same, because we have equality here. And so for we have a corollary. If we have this variety of small codimension and L2 is equal to 2c, 2 times the codimension, then we have this equality, where z is the Veronese variety, for all k starting with the 2 times the codimension, and also k2 of y is equal to n, that's the minimal possible value, and delta k is equal to k minus c for k in this range. And yesterday I even explained that in this case all the entry loci were obtained by cutting this variety y with a hyperplane subsequently. So up to this value to c. This simply shows that we have other bounds, also upper bounds in many cases for this invariant L2, and we can control what happens in this case, and many examples of such situations are given, for example, by complete intersections of hypersurfaces of degree larger than 2. They all are like this in this range, dimension range. But next, I'll turn to studying what happens if L2 assumes the value near the lowest possible. So we'll study next this case, which turns out to be important and which shows how these elementary considerations are connected with something that you probably know very well. So we have several invariants that I recalled now, and they are not independent. There are some relations between them, and now I proceed with writing some of these relations. So I define these quadratic deficiencies, and I sum up them, and we consider so the following sum. Up to K2. We sum up all non-trivial secant deficiencies and denote this by delta 2. The sum of all deficiencies, which if some deficiencies are non-zero, then this is non-zero. And so I write the following proposition. That delta 2 can be computed easily in terms of other invariants, namely the number of quadratic equations minus some constant depending on K2. So this constant is like this. And this is again a trivial computation because what do we know? We know that the dimension of the linear span of X, and this is I already wrote today. By definition, because quadratic equations become hyperplanes after Veronese embedding, and this is equal to, I recall that, again, the formula that was used already several times. We will not need this now. So I recall this formula, which is again a trivial consequence of the definition, that Sk is equal to the sum This follows immediately from the definition of second deficiencies, and therefore I can write this is a triviality. I just explain what it, because we know that sk2 of x is just this linear space. And I just explain how to compute the dimension of sk2. So this is a triviality. But it has important consequences. So the first one I write just now. Next proposition is we have the following inequality for E2 using the above proposition. Almost the same, but here I sum up to n, and we know that K2 is at least n. And of course this is, we have this inequality by simple calculation. And both inequalities turn into equalities. If and only if K2 is equal to n, minimal possible values. And now let's stop for a moment and look at what we proved. We now know that yeah.
Maybe just second inequality is equality.
Inequality.
So
this is inequality, but if we have this equality here, then we can replace n by K2. And we compare it with this one, and then we get what we know.
So why did you call the summation of second deficiencies delta 2? Or why? It's just a notation?
Just notation. I have some invariants, and if you can call it total quadratic deficiency. It's natural because you sum up all deficiencies that they exist.
So
because they start with.
What is the meaning of 2?
What is label 2 means for quadratic, because you see there is y, and y is before quadratic, and so you could consider the same thing for 1, for example, or for 3, but this is for the second quadratic embedding. And I rewrite it once more before applying to some known cases, so I can forget for the moment about this. This was the first step. Just all these are computations. It's just writing out the definitions. There is no idea in them. So finally we get E2 of y. Did I write it over here? Maybe I wrote it. So look, for example, this term, it may be positive and may be negative. if the codimension is small, then you see that this is we subtract something. If the codimension is big, then we actually add something. But anyhow, this explains that the number of equations is bounded in terms of our invariants, which I recently introduced. And as a corollary, we get immediately the following inequality. It's a trivial consequence of the theorems, also elementary theorems that I proved, these bounds that I proved. So we have always this inequality. And equality holds if and only if L2 is equal to C, the minimal possible value. Which means that we are there on the upper line in this picture. So we apply this. And equality here holds if and only if K2 is equal to N. I've written it there. And what can we say about delta K? We know, and I formulated it here also, that this sum can be bounded. Is bounded and we can sum up all these terms, and then we get immediately I'll explain just in a moment. And therefore we have this. So I need to sum up these numbers, but starting with L2. So I add this term summing from C to L2, because before C they are always 0, and we get this. This is again a trivial summation. So we have this bound, and with equality holding if and only if L2 is equal to C. And so eventually we get E2 we have this required bound. So again, there is no deep idea. No, this is just a calculation. If we know how to bound the number of quadratic equations in terms of deficiency, then we can write out the deficiency. And using these two theorems that I proved yesterday, that K2 is bounded from below by the dimension of the ambient space, and that the second deficiencies are bounded by this, and this is a consequence of the first assertion, we get this bound. Now, what we actually proved is that for any variety, we can give an upper bound for the number of quadratic equations in terms of codimensions. This is a classical result, but maybe this proof is very different from the one you usually get. And so I formulate this corollary as a theorem. So let y be an arbitrary variety, non-degenerate, say, of codimension C. Then the number of quadratic equation defining y does not exceed this value with equality if and only if C is equal to n minus n. So here we don't have any second variety, we don't have any second defects, all has disappeared, but we got some general result. C is equal, sorry. Here there is some conditions that we understand only with secant deficiency, but here we have a general result. So we maybe would like to reinterpret it somehow to understand what are these varieties. And people here probably know this very well, but if you ask someone who has even passed an exam just in algebraic geometry, usually he will not be able to answer this question, because this is in general it's not what they usually taught in the courses of algebraic geometry. And varieties, and if you ask some student who has passed his exam in algebraic geometry, he will not yet be able to answer you what are these varieties, how can you describe them. We'll give an alternative description, but I just remind you that here this condition is equivalent to delta, in our notation, delta k is equal to k minus c for k in this range. So we have all the numbers as expected, and we sit on this line. And now I'll explain why. I'll give you the answer, which many of you know, that E2 of y is equal to this maximal value if and only if y is a variety of minimal degree. This is the variety whose degree is equal to codimension plus 1, because it's immediate that for any variety y you have inequality here. This is the minimal possible value of degree for a non-degenerate variety. Of course you can have less than that, but then this variety would not span the ambient space. For example, if you take finitely many points, then you see d points and you know, in this case the codimension is equal to the dimension of the ambient space, and if d is less than n plus 1, then of course they span something smaller. So this is the minimal possible value, and it's interesting to classify the varieties satisfying this condition, and I'll explain how we arrive at this alternative description, that the maximal number of quadratic equations is the same as variety of minimal degree. So first of all, I write down the following observation. Consider a general hyperplane section of y. So y prime lies in Pn minus 1. We would like to compare the two numbers, E2 of y and E2 of y prime. how can we argue? We can say that if we have some quadratic equations, that means that y is contained in some quadric. And when we intersect this quadric with this hyperplane, we get some quadric. Can this quadric be minimal, be trivial? This would mean that y is degenerate, because then this hyperplane section will be a union of two hyperplanes. So it cannot happen. So we know that we always have this inequality, because each quadric here gives rise to a quadric here. But we don't need to have an equality. For example, consider a curve, a quartic curve C in a non-singular quadric in P3. This non-singular quadric is a product of two lines, and we consider a curve of type 1, 3. That's a rational quartic curve. So this means that C is equivalent to L1 plus 3L2. Then how many quadrics contain this curve C? It's very easy to see that there is only one quadric, namely this Q. Why? Because otherwise there would be another quadric, and the intersection will have degree 4 and would coincide with our curve. But this isn't possible for many reasons. For example, one reason is that the intersection of two quadric is an elliptic curve, but there is a different reason that this curve C, our curve C, has a lot of trisecant lines, because you see that C intersected with any curve with the first, from the first family is equal to 3. That means that it's like this, under this projection of a quadric to a line. And the intersection of two quadrics doesn't have trisecant lines, because such a trisecant line, if a line meets a quadric in 3 points, that means that it's contained in a quadric. So C is contained in only one quadric surface. But what about general hyperplane section of C? General hyperplane section of C consists of 4 points in a plane. So 4 points in the plane is contained in 2 conics, because a conic can be drawn through 5 points. And so here E2 is equal to 2. So the number of quadrics, or E2, can jump, but it's always bounded for y prime by this number E2 for y. So if we know that, and it's a simple exercise for you to show that if y is linearly normal, then E2 of y is equal to E2 of y prime, but I will not need it. What I need is that if we know, if we're interested in variety y for which we have this equality, then for y prime, the codimension is the same. This is evident. And therefore, this number is the same. And this inequality, which is trivial, shows that if y is a variety, n-dimensional variety, for which this number attains maximum, then the same is true about y prime. And so we are finally reduced to linear sections which consist of finitely many points. And we can study these general linear sections. They consist of finitely many points. And now I'll say something about such a situation. So suppose I'll show that So we would like to show that proposition E2 is equal to this maximal number if and only if the degree of y is equal to c plus 1. Suppose that the degree of y is larger. Then there exists finitely many points y0, y a plus 1. Here we have c plus 1. We have here c plus 2 points, so more than c plus 1. And we may assume that they are in general position. What does it mean? We say that a collection of points is in general position if, maybe I write down the definition. So we have some variety y, and we intersect it with the general linear space of dimension whose dimension is equal to its codimension, and we get a variety which I also can denote by y prime, consisting of finitely many points. So I say that we say that a union of finitely many points is in general position. So it lies is here. So in general position, we have d points where d is the degree, and this collection of points is in general position if and only if any collection of points like this spans the ambient linear space. In principle, it could happen, for example, that all these points or some of them lie on a line. But we say that there is always exists a linear section for which this is not so. And the proof is immediate, so we would like maybe to show this just to give you an idea of what are linear sections of algebraic varieties. I'll do this, for example, for curves. It is sufficient because first we can cut y by c plus 1, pc plus 1, and then we get some curve. And then we cut once more by hyperplane, and then we get finitely many points. So it's more than sufficient to prove this result for curves, for linear sections, for hyperplane sections of curves. And so we have a curve C, and we have points here, y1, yd, and we consider various hyperplanes. We consider the hyperplanes form a dual projective space, PC plus 1 dual, and we choose some this collection of points, which means that we choose some hyperplane here, and we consider the map locally defined of some neighborhood, defined by some index like this. have how many points? The dimension of the ambient space is C plus 1, and so we have C plus 1 points. And we have some map to a product of this, to the product of C plus 1 copies of this curve. And for any collection of points, we associate such hyperplane. Since any hyperplane meets this curve in some points, this in some neighborhood this is surjective, because we can choose any number of points equal to the dimension of the ambient space, and then we can draw a hyperplane through this point. We don't now have in mind the other points up to D. We take only the dimension of the codimension plus 1 points. And then we see immediately that linear dependency is given by algebraic relation. So here the collections that are linearly dependent form a proper algebraic subvariety, and its inverse image here is also proper. And that means that if there exists an open neighborhood for which this condition is satisfied for each index, and then we consider the intersection, and it's also an open neighborhood. So we may assume that these points are in general position. And so how we would like to show this proposition? Suppose we consider the corresponding Veronese images. And suppose that these points are x1, x0, so C plus 1. Suppose that they are in general position. These are Veronese images. I'll soon turn to explaining what is the difference between general position for Veronese images and the points themselves. Suppose that they are in general position, which means that they span a big linear space. C plus 1. Because we took C plus 2 points. Then, look, these points lie here. By the very definition. This was a linear section of our variety. And we know how to compute this dimension. I just did it, and so the dimension is equal to PC. Because it's equal to C times C plus 3. This is the Veronese image minus E2 of PC intersected with Y. And this is equal to C. And now we arrive at the following situation, that if the degree were not minimal, then this is impossible. It's impossible that these points are in general position. So let me put it down. And I'm going to show that this is impossible. This can never occur, that these points are never. So if I'll write it as a fact Now I formulate something that is violated by this proposition. Forget everything. So let us take some points in Pn, k plus 1 points in Pn. And suppose that the dimension of the linear span satisfies this inequality. You expect here the maximal dimension is k, the expected dimension, but we just suppose that it's one less, at least. Then the Veronese images are in general position. So look, if we use this, then we already know that this is a variety of minimal degree, because we just arrived at a contradiction with the fact that these Veronese images are in general position. This cannot happen. So to conclude that varieties having the maximal number of quadratic equations have minimal degree, it suffices to prove this fact. And this is a special case of a general problem which is very interesting and very important. Suppose we have any collection of points in some linear space PR. Suppose that they span PR. And we can consider the Veronese images. What is the dimension of the linear space that they span, that X sub I span? First of all, it's an very easy to realize that this dimension is at least equal to R. Because actually we can project the Veronese variety to obtain a linear space. You know this. So, but how much larger? And this is a general question which is quite important. We can apply second, third, fourth Veronese map, and the points become more and more independent. How can it happen? For example, consider the easiest case when R is equal to 1, which is very important in projective algebraic geometry. Suppose that we have 3 points on a line, and consider the Veronese image. The line becomes a conic, and these 3 points which span a line, now they span a plane. And now consider 4 points on a line again. Because this is lying on a line means that there is very little room. They are most dependent possible, if you wish. So what we see is that again the second Veronese image is a conic, and so now we get 4 points on a conic. But they span not P3 as we would like to maybe, but they span still P2. But if we take the third Veronese map, then we get 4 points on a twisted cubic, and they span a P3. So applying high Veronese maps allows us to make points more and more independent. And so I'll formulate a result, result which is not very general, but actually it's sufficiently general, and actually it's connected with some zero-dimensional syzygies, and the general problem was not so long ago solved by Green. But what I need, I'll be able to do elementary. So I formulate the corresponding result. So we consider finitely many points And suppose that they span an r-dimensional space, subspace, in Pn. And this lies in Pn, but this is not so very important. And we denote as usual xi the images, and we introduce another number. Here we have r, but also we introduce another invariant t, which doesn't exceed r, is the maximal number such that arbitrary subcollection of points, if we take t plus 1 points out of this k plus 1 points, then these points are in general position. That means that it's equal to t. And suppose that this number k doesn't exceed r plus t. Then the Veronese images are in general position. What do these invariants mean? They control how the points are distributed. For example, if you have some number of points in the plane, it may happen that 3 of them lines on a line, for example. There is a trisecant line. And this means that this number t is only equal to 1. If there are no multi-secant lines, then t is equal at least 2. If there are no, for example, 4 points lying in a plane, then t is equal to 3, and so on. So t controls how the subcollections, to what extent the subcollections are in general position. And in particular, it suffices to apply the case t equal to 1 to get this fact. Because the fact says that if they span something like this, then the images span something more, something of larger dimension. And this we get here because t is at least equal to 1, because anyhow any 2 points they span a line. And therefore in all cases r plus 1 points are always become independent. If we have one more point than is the dimension that we expect to be independent before Veronese, then all the points become independent after Veronese. This is a consequence even of this general proposition, even for t equal to 1, which means that there is no condition, because we simply demand that any 2 points span a line which is trivial. But this will allow us to go further beyond the varieties of minimal degree, and this I'll explain next time. So this is all for today.